Hi everybody, welcome back. We are continuing on with factoring quadratics. This is the last of it. We'll be able to handle almost everything that comes our way with one exception, and we'll circle back to that in chapter 6. But for now, this is the last of the factoring that we're actually able to factor. Now, this is considered a special case, but we already know how to do this. So what makes this special? Well, if you look at them, because they are the same, we write them out with an exponent. So it's not really a special case. However, it does have a special way of being written. Likewise here, we know how to do this. Give it a shot. Okay, so there's no common factor. What is that? That's not 9 and 3. 9 and 4 would be 13. All right, I'm having a mental block for some reason. Right, 6 and 6. So it's a more complicated version of the last question, but it's pretty much the same thing. Now, where we do get into, oh, wait a second, no, we're continuing on with the perfect squares. My apologies. So when a trinomial can be factored and the result is a binomial squared, the term for that is perfect squares. We've already looked at two, and like I said, we've done them without realizing that that's what we were doing. Personally, I don't really care about this because I would just go through with the RS or the ARS and solve for it. But it does come up, especially with more complex stuff. How can you tell that a trinomial will be a perfect square? So all of these are perfect squares. So how would you identify that it's a perfect square? And the answer is your C, right? Remember this is a C, is a square value, and B should be the square root. Okay, so if we notice, square root of 16 equals 4, B equals 2 times 4. Square root of 36 is 6. Now, we haven't really dealt with it, but the proper answer is that it's a plus or a minus 6. 2 times negative 6 is negative 12. Okay? So if you want to be keen and identify, hey, this is a perfect square and save yourself some work, go ahead. Personally, I'm too lazy to do that extra memorization. Now, differences of squares are a little different. This one actually does require memorization. These follow the pattern, but they're unique. Now, how do I know that RS equals 0? And the answer is, it must be 0 in the middle, because 0 times x is 0, and we don't usually bother writing in x squared plus 0 minus 1. We would just shorten it down. Okay, so it's a bit of a memorization thing there. But if we keep that in mind, two numbers that multiply to -1 and add to 0, well, that's +1 and -1. All right? Now, you do want to get in the habit of memorizing that trick. And we'll get into why in just a second. I know, you're all at the edge of your seats waiting to find out why. Oh, hey, look at that. I've already given away the pattern. Oh, I love me my Calvin and Hobbes. So if we square root the first value, square root the second value, you get the numbers. So what it gets you the numbers. You still have to remember that it's a +1, well, +1 value, in this case a 5, and it's a plus minus the second value. I did it the reverse of what I said. Doesn't matter. One's adding, one's minusing. As long as you remember to get both of them in there, you're good. So why is that pattern important? Well, what happens when you get the goofball questions like this? These don't follow our regular pattern. We could make them follow our regular pattern, but it's so much easier just to go square root of 16, square root of x. And you're done. I don't often advocate for memorizing blanket information, but this is one where it really is easier to do math. It really is easier to memorize. Now, you still have to common factor ahead of time. You still have to make everything work. But yeah, that's the gist of it. The last question here, question number 10 AC, is optional. So if you want to do it, that's great. I do recommend it, but it is not mandatory. Okay, so as you can see, this lesson was originally meant to be give or take St. Patty's Day. So happy St. Patty's Day.